Alright, so we are going to talk about things called Kuratowski closure operators. Okay, so it's just a map on the power set of X that satisfies these four conditions. And so we're calling it a closure operator. So you might think, okay, well, if we think about the definition of a closure in topology, hopefully that should be a closure operator. And that's exactly what Part A says, or Part A wants us to prove. That if we're given just a topological space, then this map that takes a set to its closure is indeed a Kuratowski closure operator. Okay, so here we know. So if you take the closure of the empty set, that's going to be just the empty set. And then for any sets A and B, A is always going to be contained in a closure. We've talked about this. And if you take the closure, if you take a closure and then take the closure of that, well, the closure of a set is a closed set, and the closure of any closed set is itself. And so a closure is just a closure. Okay, so that's the first three conditions. And there's one more remaining, and it says to use exercise 11, so we better use that. And in fact, that's just straightforward. The closure of this union is equal to the union of the closures by exercise 11. Alright, and that's part A. That's all we had to do. So again, exercise 11, it asks us to prove that a closure of a finite union of sets is equal to the finite union of the closures of the sets. And so this just proves that. Because this is just the case of exercise 11 where you're only dealing with two sets. And in fact, you can just, if you wanted to, you could extend this condition 4 to the finite union case because you just do induction. But here, like, just doing it for the pairwise case is shorter to write, and you can deduce the finite unions from this, so that's fine. But yeah, that's all we need for part A. So if you have a topological space, then this closure definition that we've come up with is a Kuratowski closure operator. So the more interesting thing is the reverse. Is that if you have a Kuratowski closure operator on a set, then this gives you a topological space. And I think this is a really interesting part because this gives us a different way of actually obtaining a topology or a topological space. And this actually, I believe Kuratowski, I believe all of this stuff is in his thesis. I believe, I don't know. I looked this up on Wikipedia. But yeah, it's interesting. So basically, the idea here is, given a Kuratowski closure operator, we're going to let F be the set of all subsets of X, which are equal to their closures. And when I say closure here, I mean like A equals A star, where star is this Kuratowski closure operator. And then this fancy T is going to be the collection of all sets whose complements are in F. So F here is our collection of closed sets, because if we think in standard topology, we know that the closure of a closed set is closed, or the closure of a closed set is itself. So we should expect that this F sort of represents all the closed sets, because these are all the sets whose star is equal to itself. And we also know that closed sets are complements of open sets. And so to get the collection of open sets, we should just use this fancy T here. And so if we think that this should be the collection of open sets, then what we want to prove is that it's a topology. And furthermore, we'll get to this, but this Kuratowski closure operator is the standard closure that we have defined in a particular topology, i.e. the Kuratowski closure of a set is equal to the intersection of all closed sets which contain that set. And of course, when I say closed sets, I mean sets taken from this set F, but we'll get there. Anyways, for now, let's prove that T is a topology. So the entire space, so let's see, we need the entire space to be in T, we need the empty set to be in T, and then we need closure under finite intersections and arbitrary unions. So X is in this fancy T because the empty set is the empty set star, and that's just the first Kuratowski closure operator condition or property. Okay, so this thing tells us that the empty set is in F, and so that tells us that if you take its complement, which is X, that's going to be in T, because T is defined as the collection of sets whose complements are in F. Alright, so that's how we prove that the entire space is in T. For the empty set, using the second condition, we know that X, the entire space, X is contained in X star, but certainly X star must be contained in X. X star equals X, and that tells us that X is in F, and so that tells us that the complement of X, which is the empty set, must be in T. Alright, so there we go. We've got the entire space and we've got the empty set. Okay, so now let's do closure under finite intersections. Closure under finite intersections. Suppose we have finitely many sets A1 through AN, which are in T. So we know that if we take the complement of any AI, then its star is going to be itself, because that's what it means to be in F. So AI complement star equals AI complement. And this holds for all I between 1 and n. So let's take the intersection of the AIs and take its complement. So what we want to prove here is we want to prove that the intersection of the AIs is in T, which means that we want to prove that the complement of the intersection of the AIs is in F. So this set here, this intersection of the AIs complement, we want to take its star and end up with itself. Okay, so let's try to do this. So the complement of the intersections equals, and then we use, what is it, De Morgan, I believe? This becomes the union of the AIs. And now we're actually going to use property 4. So this is going to be equal to, no, we're not using property 4 yet. This is equal to the AIC stars, because we just proved that this holds for all I. And now we're going to use the fourth property, but extended to finite unions, to prove that this is equal to the union of AI complement star. Alright, so we have this. So then, let's take the star of this entire equation, and I'll just write this as AI, then I'll write complement star. You could put an extra set of parentheses around this, I don't want to. But then what we're going to end up with is the union from 1 to n of AI complement, and then we have star here. But then, if you take star twice, that's the same as taking star once. So this is the same as this set. But then using the equation from the previous paragraph, or sentence, this is just the intersection complement. Okay, so if we take the complement of the intersections and take its star, then we end up back at the complement of the intersections. So this means that the intersection, the AI's complement, is in F. So we have that the intersection, if we take the complement of that, which takes us back to the intersection, this is going to be in T. And that's what we wanted to prove. Now, this next part uses a fact that I actually had to look up on that Wikipedia page to figure this one out. There's actually sort of like an intermediate fact that you need to use here, which once you realize it, it's sort of straightforward. But it's what you need here. So note that basically what we need to confirm is that Kuratowski closure operators work with, or they preserve inclusion. So if A is contained in B, then A star should be contained in B star. So B star can be written as, okay, so A is a subset of B, so we can write B as a disjoint union of two sets of A, and then all the set of elements which are in B but not in A. So we have this star, but we know that star commutes with unions, and so this is A star union B set minus A star. And so this is certainly going to contain any set involved in this union. So this contains A star. And there we go. Alright, so now we can move on to proving a closure under arbitrary unions. So suppose we have an arbitrary collection of sets AI in T. Then, again, AI complement star equals AI complement for all I in whatever set we're indexing over. It could be an arbitrary set. Okay, so what do we want to prove? We want to prove that the union of the AIs is contained in T, i.e., the complement of the unions is contained in F, i.e., by De Morgan, we want to prove that the intersection of the complements star equals the intersection of the complements. Now certainly, if you take the intersection of the AI complements, then this is going to be contained in a J complement for all J. Right? Because if you're taking an intersection, the intersection of a bunch of sets is going to be contained in any particular set that you're taking the intersection over. Okay, so we have this inclusion, and then we can put stars on both sides of this inclusion. So the intersection of all the AI complements star is going to be contained in AJ complement star. But AJ complement star is equal to AJ complement. Okay, so if you take the star of the intersection of the AI complements, that will be contained in every particular AJ complement. So if it's contained in every particular AJ complement, then in particular it's going to be contained in the intersection of all of the AJ complements. So if we take this inclusion and take the intersection over all J's, it will still hold. So the intersection of AI complement star is contained in the intersection of AI complements. But certainly the intersection of the AI complements will be contained in the intersection of the AI complement star, because that's one of the Kuratowski closure operator properties. And thus we have equality. So the intersection of the AI complements is equal to the intersection of the AI complements star. So this proves that the intersection of the AI complements is in F, which means that its complement is in T, but its complement is the union of the AIs. So this proves that the union of the AIs is going to be in T. And this holds for any arbitrary collection of sets AI, and so that confirms closure under arbitrary unions, and hence T is a topology, or a topological space, when you pair it with the set. However you want to say it. Okay. Now there's one more thing that we have to do, and thankfully it doesn't take too long. But we got to prove that... So let's write out what we want to prove. Lastly, we must prove that for all subsets A of X, we want the Kuratowski closure operator of the set to be equal to the standard definition of closure in a topological space. So the Kuratowski closure of a set is just A star, and then the standard definition of closure is just you take the intersection of all closed sets such that the closed set contains the set in question, which is A. And again, like I said, the closed sets are going to be all the sets. We're going to, in this case, we're going to define them to be all sets whose Kuratowski closures are themselves. And so that's how we come up with this definition. Alright, so we want to prove this statement. Okay, so one direction is easy because A star is in F, and A is a subset of A star. So certainly A star is going to be contained in the intersection of all elements of F such that B contains A, because A star is one of the sets that we're taking, it's one of the sets that we're taking this intersection over. And since it's one of the intersections, it's one of the sets you're taking the intersection over, then the intersection is going to be contained in that particular set. Okay, so that's sort of the easier direction. For the other direction, for any element, for any closed set such that this closed set contains A, then what happens if we take the star of this inclusion? Then we get A star is a subset of B star, but since this is a closed set, it's equal to B. And so what this tells us is that A star is contained in every... So if we look at this set on the right here, the set of all B and F such that B contains A. This collection of sets, every set in this collection of sets contains A star. So when you take the intersection, that intersection will also contain A star. And so A star must be contained in this intersection. And so we have by inclusion. So hence, A star equals the intersection of all B and F such that B contains A. And so yeah, like I mentioned before, this is neat in the sense that it gives us another way to define a topology. Instead of starting with the definition of an open set and building up the topology from there, we actually start with the definition of a closure operator. And then once we have this closure operator, we define closed sets to be sets whose Kuratowski closures are themselves. And then once we have closed sets, we can take their complements to get open sets. So this is sort of a neat idea. And in fact, when I was looking at the Wikipedia page, another interesting thing is that we have these 4 conditions to be a Kuratowski closure operator. Apparently you can combine all 4 of those into one single condition, which ends up being equivalent to all 4 of those. And that's, I looked at it and it seemed pretty counterintuitive, like how this would be equivalent, but like I'm sure it's been done, and it seems pretty interesting that you can reduce the number of conditions like that. But yeah, that's all we need to do for this exercise, and so we're done.